In the category of set, if we have two objects or two sets, we fix them as the source endpoint and the destination endpoint. We can explore the home set from X to Y, or written as YX. It is of special interest if we fix one endpoint, like we fix X equals A. So if that fixed, given any set Y, we can have or we can fix the other endpoint so they're called the home functors. In linear algebra, we usually consider this kind of home functor. It's called a contravariant home functor. And we'll explain the meaning of contravariant and here the covariant future. So it's a little bit abstract, but we can consider like this. If we have X as a set, we want to study the X, but the information we can get from X is nothing but is cardinality. It's a number, right? It's an extended number. But we're not satisfied with so simple structure. We want to build a more sophisticated structure over X. So how? A usual idea in mathematics is to given A also as a set, but a set with a better structure. We'll give examples in future. Anyway, we have a set, but with the set A equipped it with a mathematical structure. And then we have A here, we have X here, any kind of, any X. We have X here. To study X, we can make function from X to A. A is fixed from X to A. From the collection of all the arrows or functions from X to A becomes AX, or set XA, or home XA. Usually we use another notation like this, from set to set, from X to BX. We use another so here is HAX. So HA is a functor. So HA is functor. It maps X to A, but it also maps Y to Z to A. So this functor HA from set to set is decided by this A, fixed A, with X to HA X equals Y, Y, and Y. So this is a covariant home functor, HA. So in mathematics, the structure of the fixed set A usually embodied in the set, the home set, or the set of functions from the set to A. And we can study it using the sets we learned before. If we have A equals the empty set, we have nothing to study here, right? So if we have A equals a singleton, say 1, then HA, it maps a set X into HA X equals the functions from X to a singleton, So if X equals AB and it maps to the singleton, there is only one possibility. So it can also be written as 1 X. You can see that the cardinality of 1 X equals to 1 and X, and is 1 and 2 equals 1. So because here is 1, so we always have a unique function from any set to the singleton. So it's trivial. Then we have 0, we have 1, and the first non-trivial example is when A equals 2. Let it be 1, 2, or 0, 1, or true, false. For binary set, the contravariant home functor, we can write it as H2. It maps from any set into H2X equals 2X equals set from X to 2. So take it as example, like AB can be mapped into 0, 1 equals 2. So the map is not unique. A can be mapped into 0 and also can be mapped into 1. So there are 2 possibilities. B can be mapped into 0 and B can be mapped into 1. There are 2 possibilities. So totally 4 possibilities. And if we have Y equals ACE 0, 1, we can calculate that that 2 times 2 times 2 equals 2, 3 equals 8 possibilities. So the cardinality of the home set is the cardinality of 2 and with the power kinetic of x. Good. Okay, so the functions here are binary valued function. This kind of function is called a characteristic function. If we define the function over the power set, so let's review the concept of a power set. Let x equals a, b, c. The power set of x is the set of all the subset of x. It can be enumerated as the empty set, 3 singletons, and AB, BC, CA, and the whole set. 1, 2, 3, 4, 5, 6, 7, 8. Totally 8 elements. So the power set, cardinality of power set is 8. So what's the characteristic function? Characteristic function is defined on the power set. If we have a characteristic function like chi a from Px, oh, I'm sorry, I made a mistake. A characteristic function is defined on the set. So a characteristic function chi is from a set X to the binary set. We have an element X. It is mapped into the chi X, and it could be valued 0 or 1. So if we have ABC by the characteristic function to map into like 1 or 1, A maps to 1, B maps to O, C maps to 1, then we get then it forms a subset. It forms a subset of A and C. B is excluded because here the value is 0. So we have subset AC, call it A. So AC. So denoted A, you can see that if X not in the subset A, it is 0. If X is in the subset A, is 1. So take away. A subset is 1-to-1 correspondent to a characteristic function. You see, a characteristic function defined the value of the characteristic function defined a subset, and the subset by this way define a characteristic function. So how many characteristic functions do we have The answer is here. Here we have x equals ABC, so cardinality of x is 3. So the characteristic function, the home set here is 8. This 8 is the number of characteristic functions, and it's also the number of all the subsets. So the power set, the cardinality of the power set is 8. This 8 is this 8. So we have one-to-one correspondence or isomorphism between the power set and the set of characteristic functions. Okay, by this way, using a covariant, a contravariant home functor, we can make any set into the set of functions from that set to the binary set, denoted like this. It is essentially the power set. So the theory of power set is studied by the home functor. This is the first non-trivial example that how home functor can help us to do mathematical research. And since we have denote a set using the vector, and we can see a subset here. Let's write down here. A is a subset of X, so AC is a subset of ABC. So if we limited our research into X itself, we can always have x1, x2, xn. We always have a vector space, X cardinality dimensional vector space. And this vector space is binary valued. So it's a binary string. Actually, it's binary string. So the power set has 8 members, empty, the singleton here, etc. So we can always denote it as the empty set. Nothing belongs to the empty set, so it's 0, 0, 0. And the singletons, A, 0, 0. B, C, and the whole set X. Good. So this is the power set is actually the illumination of the whole vector space. And further, when we studied the real or complex linear algebra, we're using the same notation. So this vector space, let the cardinality of the set is M. M is a cardinality. So the vector space, the binary value vector space is denoted as QM. So this vector space is isomorphic to the function space. So we have the power set isomorphic to the home set of characteristic functions and isomorphic to the m-dimensional binary valued vector space. So these terms can be interchanged without any trouble. We can see that the dimension of the power set, or the dimension of the set of characteristic function, or the dimension of the vector space is M. M is the cardinality of the set X. And finally, we talk about basis. We have 3 singletons in the power set. So given any set X, if X has a cardinality of M, it has M singletons. And the singleton is represented by a vector with only one non-zero element. So formally we can denote it using like a Kronecker, right? Kronecker. When I equals j is 1, otherwise it's 0. Okay, so if we list the members of X as x1, x2, and xm, finite or infinite. So any element xi it can determine a singleton xi. This xi can be represented by 0, 0, and 1, and 0. 1 is at the index of I. So we have m singletons. We have x1 equals 1, 0, 0, and x2 equals 0, 1, 0, blah, 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 xm 0, 0, 1. And all the singletons of a set forms a basis of the power set. We have not talked about linear algebra, but we have already understand what the concept of basis is. What's the meaning of the basis? If we have a subset called AC, which is a subset of X equals A, B, C, for example. So AC can be written as AC or written as 0 or 1, 0, 1. B is excluded, so it's 0. So this one can be expanded into 1, 0, 0 plus 1 times 1, 0, 0 plus 0 times 0, 1, 0 and 1 times 0, 0, 1. And they are the basis from the singleton A, singleton B, and the singleton C with binary coefficients. So the basis, they are the basis. The basis with the coefficients can generate a subset. You can try and you will find for all a subset in the power set of X, the singletons can generate A. So this is a philosophy in mathematics as a free generation. The free generation from a set, from a basis, to generate a vector, any vector. Subset is a vector. So the basis can everything it generated together became a vector space. The vector space here we talked is the power set. And in future, we can generate more complicated mathematical structures. And the free generation is achieved by the covariant, the contravariant home functor.